Good afternoon. My name is Andrew Thornburg, and I'm going to be presenting an interactive poster that was presented at the 2015 ICC conference in London. My co-author is Tianyang Bai, and my advisor is Dr. Robert Heath. So we wanted to motivate millimeter wave networks in terms of the amount of bandwidth that is available. All currently deployed bandwidth from 300 megahertz to 3 gigahertz fits in this very small portion of the millimeter wave spectrum that is the 802.11ad ISM band. So with that massive amount of bandwidth that's available down here, what can we do with it? And what type of millimeter wave assumptions affect the performance? So there's two main differences with millimeter wave networks as compared to lower frequency UHF networks. First is that the use of directional antennas is almost required at the transmitter and the receiver. Because of the shrinking antenna size, large antenna arrays will be used at millimeter wave frequencies, which result in these very directional pencil beam antenna patterns. Secondly, blockage can and will reduce interference. As you can see here, these two users, which are currently pointed at each other, are heavily shadowed with this building from the nearby interference. So the question that we answer in this work is, how do these assumptions affect the performance of a millimeter wave ad hoc network? Here is an illustration of the network in question. We have a typical receiver and a typical transmitter, each perfectly aligned with each other. We have buildings that are randomly scattered according to a Poisson point process with a random width and orientation and length. And then the transmitters that are interfering are also distributed according to a Poisson point process. And there's not that many references for outdoor large-scale millimeter wave ad hoc networks. Most of the current work is with the application of millimeter wave to indoor PAN and LAN networks. There's immense work with stochastic geometry with ad hoc networks for lower frequency networks, particularly with directional antennas. Our work differentiates in the sense that we include the blockage model in this. And there's been a lot of work on cellular millimeter wave networks. So the motivation that we came up with is how can we evaluate a millimeter wave ad hoc network? So we have three performance metrics that we evaluate in this paper. First is, what are the chances that you are connected to your peer? Basically, that receiver that is a fixed distance away. So we quantify that with the SINR CCDF. So the probability that the SINR is greater than a threshold. And that threshold is set according to the application that you need. Either it's voice, which requires some sort of low data rate, or perhaps streaming video, which will require a higher threshold and larger data rate. And secondly, how dense can the network be while maintaining this connection probability, which is referred to in the literature as the transmission capacity. So as a function of the receiver distance, the SINR threshold, and the outage, which is just 1 minus PC of t, you can solve for the transmission density, which is lambda. And basically what this means is how dense can you pack these nodes. And lastly, as a function of the transmission capacity, what is the aggregate rate achieved by the users, which is known as the area spectral efficiency. So we have users per area getting some rate according to Shannon's equation, and then some percentage of the time, 1 minus epsilon. So here is the main quantity that we manipulate in this work. It's the SINR of the millimeter wave ad hoc network. So we kind of parameterize it in this way. We have the power and path loss intercept, which is accounted for by P of t. We assume that the main link is aligned, which is ongoing work that we're still working on as far as how does that affect the performance. We assume that the transmission link is fixed at distance r, and we assume that the ideal transmission is line of sight. And we have the same parameters essentially down on the bottom for all of the infinite interference. We have random gain, which is randomly determined according to three possible outcomes. Either the interference is aligned with the typical receiver, the interference is pointing at the typical receiver but in the side lobe, And then lastly, and the most common, if the beam width is sufficiently small, that the side lobes are pointed at each other. And we use a gamma random variable as the fading. We have a random distance, di, according to the PPP. And then we have a blockage model which differentiates between line of sight and non-line of sight. So if it's non-line of sight, the path loss exponent is 4, and if it's line of sight, the path loss exponent is 2. So here are the results for each of these three metrics. So what we have here are two different networks with the SINR CCDF plotted. So first we have 50 user pairs per kilometer squared, and second we have 500 user pairs per kilometer squared. And as you can see, the analytical expressions that we derived using stochastic geometry fit quite well to the simulations that we used. In addition, the SINR CCDF is heavily towards high SINRs. So at 25 meters, there's a 90% chance that the SINR will be greater than 20 dB in an outdoor network with this density. Conversely, increasing the user density by 10 reduces this chance by about 10 dB. So 90% chance that 25 meters has a SINR greater than 10 dB. So transforming that equation, we can solve for the transmission capacity. And what we have here is lambda here, which is the density. So this, keep doing that. This corresponds to 1,000 user pairs per kilometer squared, and this value over here is 100 user pairs per kilometer squared. And what we see here is that we get a 10x density increase at 0 dB as compared to a UHF network at 2.4 gigahertz. And what is interesting is that if plotting the area spectral efficiency, you see these peaks here with the millimeter wave networks, which implies that there is some optimal SINR threshold for efficiency, is that the best density occurs here, which is actually an extremely, extremely dense network. It's 1,700 user pairs per kilometer squared, which is orders of magnitude higher than the UHF network. We have about a 10x efficiency improvement and a 10x density improvement. And what we have here is a plot of the SINR curves from here, assuming full interference and noise and just the line of sight interference. So what this is showing is that the network is heavily line of sight interference limited, meaning that you can ignore the noise and the non-line of sight interference when considering a network of this type. And lastly, we have a rate coverage probability, which is essentially this curve transformed into a rate. So given an SINR, a user will achieve such a rate given that the bandwidth of the network is, for the millimeter wave network, we use 100 megahertz. So here it just shows that millimeter wave networks can achieve massive rates with a very high probability. Here, the 25-meter network with the 90% probability will achieve over 500 megabits per second. So in conclusion, we characterized the millimeter wave coverage and capacity. The main takeaway from this is that the physical propagation of millimeter wave significantly reduces the interference strength, which can enable a dense, high throughput ad hoc network. And the main extensions that we are currently working on is relaxing the LOS requirement for the typical link, which we do in the journal extension of this paper, a different blockage or PPP model, so either we could cluster the users rather than uniformly distribute them as a Poisson point process. We only account for single hop here. How does that affect with multi-hop? And then taking all this theoretical work and putting it into a prototype and protocols. And here are some references that we referred to earlier. Thank you.